significant improvement, like in terms of the outside.
Okay, so we start with the second day, and the first speaker today, the first speaker of the day is Vijay Saraswat. So Vijay got his PhD from Carnegie Mellon University, and under the supervision of Dallas Scott, I'm sure you know who that is. And for his thesis, he got the ACM Doctoral Dissertation Award that's given out for the best thesis in computer science for work on studying properties of concurrent constrained programming. So later he became a professor at Penn State, and after that, I think probably around 2003 or so, he joined IBM Research, IBM Vijay Research, and there he's been leading the design of this X10 programming language, parallel programming language, and the distributed parallel programming language, which has been quite impactful. There's been various interesting concepts there that have been developed, and the work has been really quite cited. So today he'll tell us more about it.
Thank you so much. You okay?
Yeah.
All you got?
All right, thank you. And we will gracefully jump over the gap of 10 years in my resume. Yes. Just one mind. Okay. All right, so it's my great pleasure to be here. It's the first time I'm visiting this department, and I'm delighted to have this chance to, after the great set of talks yesterday, to hopefully continue today on a slightly different topic. The focus here, as you see, is going to be on programming languages, concurrent programming languages designed for resilience. The work has been done with a number of people, mainly from the X10 group at IBM, but also colleagues at the Australian National University and Sylvia Crafa at Padua. As Martin Reinhardt has taught us, each talk must begin with two cats. So, here are a pair of cats from my friend Francesca Rossi at University of Padua. And what Martin has also taught us is that all greatness in computer science is because of your students. And that is actually completely correct. And I'm glad to have two of my students here today. Not my students, two students that I've worked with when they were students here today. Now, the question for you is, which is a cooler pair of cats? There's a blonde one on the left, and there's a raven-haired one on the right. Which is cooler? So think about this while I go on and I talk about some very mundane stuff. Okay, I should have asked for a vote, actually. So I'm going to talk about a concurrent programming language, X10. That we started work on this actually in 2004, so it's been about 10 years. And I've been in industrial research labs at Xerox Spark and AT&T Research and IBM for over about 20 years altogether. This is by far the longest industrial project I've been involved with. And it's still going on, and I'll give you some reasons why it's still going on. So this was a language motivated by, there was funding from DARPA, motivated by a very simple problem. And the problem is, as you scale out, and particularly for high-performance computing, you're looking at programming, writing code that runs on 100,000 cores. And now when you go off to the Tianhe computer, you're talking of millions of cores. So you got to, we talk about correctness and reliability. Tell me how you're going to debug code running over 5 million cores. So you've got to really get a very different mindset. And with X10, we're not at that mindset yet. Very different mindset when you're writing code that's going to scale enormously to millions and millions of cores. So with X10, our goal was, at the end of 2010, we were supposed to, IBM was to deliver this machine, and we did, the Perks machine, a little bit late, but we did. It was going to go up to 100,000 cores, and our goal was to design a programming model, implementation, which would run at scale on it, and not reduce the level of abstraction to MPI, OpenMP, and later CUDA came into play. So that's what X10 is. It's more or less a fairly traditional language as far as implementation is concerned. There's a compiler front end, ASTs. You compile out to two different backends, a C++ backend and a Java backend. And this was also a very unusual aspect of what we did, a single language. The source language, roughly speaking, think of it like Java. It's high level. It's high level from the viewpoint of Java-like languages. It's object-oriented. It's got all the sequential constructs that Java has. One innovation we did do in the sequential part was a dependent type system, and that has many interesting things, but that's a different track, so I'm not going to go there. But the main concepts that we introduced all had to do with concurrency and with distribution. So that's really what I'm going to focus on. It's open source, available X10 Lang org. We just released 2.5 version yesterday. It runs on all kinds of systems. Here are the core ideas in the language around which everything is based. They're just a handful of constructs. It's organized around places and asynchrony. What's a place? Think of a JVM, a process, as a place. It's got some representation, I mean an operating system process. It's got some representation for data inside it, some representation of multiple threads that are running inside it. But you're not going to run one operating system process on 100,000 cores. You're going to have to go to many such processes working. So this was a major decision we made in the design of X10. We are going to surface a non-homogeneity in the memory structure to the programmer. So the programmer is aware that their single piece of code is going to run on potentially a large number of places, 10,000 places. And then the question arises, what are the new constructs that you introduce in order to make this available? The first thing you have to answer is, what's the structure of memory? And what we decided was that we are going to use what is now called a partitioned global address space model. In other words, what you have is you have references that can go across these places to memory living in other places, and you have operations that can use these to get things done. I'll talk about them in a second, but we are not relying on MPI style or CSP style handshake communication for communication between code running in these places. So you got places, and places have these global references going back and forth. And then the second major point was to focus on asynchrony. Remember, this is back in 2004. This was sort of a big step at that point. Today, with the exascale computing stuff, everything has got to be asynchronous. So we are lucky that we've actually designed the language and implementation which really focuses on taking advantage of asynchrony right from the get-go. So async S. S is a statement, async S is a statement. What does it do? It runs S in its own separate task. Task because you will have a bunch of operating system threads that you have pulled into each process, and we're going to do two-level scheduling. You want to have finer-grained tasks that can be supported at the level of the threads available to you from the operating system. But you have places. How do you compute across places? Very simple single construct, orthogonal to async. It says, I'm going to go move to place P, and I'm going to execute S there. And when I execute S there, this is a synchronous operation. If I wish to make this asynchronous, as you often do, and I'll have idioms showing that, you simply combine it with async, HP async S, for example. A crucial thing to async, and this was a major innovation in X10. Silk had something similar, but with significant restrictions, and Silk did not work across multiple places. Significant innovation here was to introduce the idea of finish. If you look at async, async lets you go from one to many. You've got to bring them all back into one. You've got to bring them back in a way that is completely predictable and as deterministic as you can make it, and completely deadlock-free. So finish S simply says, I'm going to run S. During the execution of S, my computation may spread out across all kinds of places using at. May spawn things asynchronously using async. We're going to wait for all the asyncs to terminate, and then finish S will go on. So just single-sided global coordination construct. Clocks are, I'll have a little bit more to say. Clocks are essentially dynamic barriers, and they are a straightforward extension of that, which allows not just detection of termination, but detection of quiescence. Of course, the key point in finish S is that in the context that I'm talking about, finish S is very easy to use and a bear to implement, because you essentially have to do distributed termination detection to implement finish S. Again, remember, these are block structured. So finish, at, async are arbitrarily nested. So you start with a single activity running a piece of code, and it can spawn all kinds of complicated communication, children across places, going to one place, coming back to where you are, and so on and so forth. And finish has to deal with all of this complexity. There is a question of how do you coordinate access between multiple activities operating on the same data structures? And we went the route of saying we'll use conditional atomic blocks. So when S is a conditional atomic block, when the condition holds, C holds, it's a condition against memory. Execute S, checking the condition, executing S, one single step. As far as all other competing atomic blocks are concerned. Again, this was in 2004, before the stuff came out around STM and around weak and strong atomic blocks and so on and so forth. So these are the core constructs that we are going to work with. More or less everything else in X10 is built up using these constructs. Please.
I presumably worry about failures, just nodes copying out, or even
That's what this talk is about.
Right. So then, how does the finishes
We'll come to
working
that.
with buffers?
So, it's good that you brought it up. Let me bring in one very simple and a crucial point. Go ahead.
I have a question. So I can specify where this S runs. Right?
Yes.
So
You do that
is
just
it,
through
is
this.
it the same as task migration, that means you move everything with a context and then come up with?
Okay, so let me give you a little bit more detail. So here's what ATPS does. Again, remember, everything is block structure. So what you're going to
Have in S is you may have variables that are defined in the lexical scope outside ATP. So they're effectively describing a binding context that you need to move over to execute on S. So the compiler and the runtime work together to take as root those variables and serialize all accessible state into a buffer, ship the buffer over, ship the code over. Well, the code is already there, so point it to the code, and then recreate that context over there and run it. That's what we have been doing since 2004. I'm not sure which other systems you're referring to. Okay, but let me quickly, oh, by the way, from here, Christoph von Prawn, any of you know him? Remember him? Yes, he contributed a lot to X10. He was one of the initial people who worked on it. So Thomas Gross's group, through Christoph von Prawn, has had an effect on our design of our system. So the key point here is this: Java exception model. So we rely heavily on having exceptions and using exceptions. The Java exception model essentially drops exceptions on the floor when they escape the stack of a thread. And that's a no-no, particularly when in a context like us, we really care a lot about deterministic execution and not introducing anything arbitrary in our control constructs in the language design that will prevent determinacy, that will cause deadlocks to happen and so on. So what we did was we realized that the reason you drop the async, or you drop an exception when you escape from an async is because you don't have a reliable way of locating that exception somewhere else, which is responsible for the control flow. What finishes that guy for us? So we collect all the exceptions thrown by the underlying guys at finish, and we have, let's just call it a delayed exception model, because finish collects these exceptions and then throws a single exception when everything under it has terminated that has all of these exceptions all together. This decision that we made in 2004 turned out to be critical for us to actually reflect back, and I'll give you a preview. What we do is, of course, we have to admit in resilient X10 the possibility that a place will die, arbitrarily on its own, just vanish. So we deal with it as if the acts running at that place synchronously through a dead place exception. And then we catch that dead place exception and define what must happen. So we ride heavily on exception semantics in order to handle resilience. Okay, any more questions on this? This is the basic set of constructs, so it's sort of important people understand this. Everything else builds on this. Okay, very quickly, I don't have time to go into this in detail. This is sort of enough. You can build up everything, not just from a point of view of semantics, but also from the viewpoint of efficient implementation, using various combinations of at, async, finish, when, and so on. Our goal was to design a language that could be as clean as we could make it, but it had to be real. People had to write real code, large pieces of code, and that's why we chose an object-oriented framework to begin with, so that you could build large libraries that could be reused by, X people writing it, Y people using it. X and Y are not the language people. So so everything here is intended to be not just clean, but also implemented in such a way that you get performance. And in terms of performance, our biggest benchmark, I don't have time to go into it, I'll just mention it, is Olivier Tardieu led the effort to implement X10 on the big supercomputer I talked about at IBM. And we've run programs at 55,000 cores on this supercomputer with actually really good performance compared to the MPI baseline code. So this is all available in a PPOP paper earlier this year, X10 at scale or AP gas at scale, that describes that stuff in more detail. Okay, so this is what is going on with the combination of these guys. And let me quickly mention clocks. So clocks turned out to be very, very interesting from the viewpoint of conceptual viewpoint as well, from the viewpoint of complexity of analysis, static analysis of clock-based programs. So clock is a barrier. It's a dynamic barrier. What's a barrier? A barrier lets you say there are a bunch of activities that are registered on this barrier. And when those activities have all reached a particular point in their code path, where, for example, they are executing an advanced all, when all of them have reached an advanced all, then all of them can progress. And they have to wait until everyone reaches that advanced all so that they can progress together. So it gives you essentially what I call phased computation. It lets you introduce, in some senses, some of the data flow ideas, it lets you introduce here. I call these clocks because of earlier work that I had done in the synchronous languages world, where there is a very important underlying notion of clocks that you have to work with. And so the main point here is that these clocks work in a context, a dynamic context. You can spawn more activities dynamically to be registered on this clock, and for the activities can die at any time. So you have to account for these operations in such a way that you do not introduce indeterminacy or deadlock as far as these constructs are concerned. Remember, we are working on top of imperative programming. So you're going to have indeterminacy if you introduce race conditions. What I'll talk about is that there are some ways in which you can program with discipline so you don't get some race conditions. Okay, so, let me quickly say what the technical results are that were a bit surprising to us around clocks. So first with Tomofumi Yuki and Paul Futrauer and Sanjay Rajapadhyay, we showed in PPOP 13 that it's possible to statically analyze completely the concurrency structure in the polyhedral subset of X10. Polyhedral analysis was done for sequential languages before. So we showed in our paper it could actually be extended to the X10 construct that I've shown without clock. And that's the 13 paper. So finish async. At is not a problem in this context. Places are not a problem. And we showed we can do precise statement-wise and instance-wise analysis. So we could do precise race calculations in the context of array programs as long as the polyhedral condition was obeyed. And there's no problem with the complexity of that computation. You introduce clocks, turns out it now becomes undecidable. And so again, what I'm talking about is there are no pointer issues here. I'm talking about static control constructs and their determination of whether, and you got arrays, and we won't talk about aliasing of arrays, we'll talk of integer subscripts for arrays. And the reason is because basically you can count with clocks. And remember I said phases. So you count with clocks, and now you get into polynomials, and you get into the Hilbert's, into the 10th problem, you get equality of polynomials. You've got to figure out if there are zeros or not. That's what you get into when you do a static analysis with clocks. So it was very interesting to us. We went from nothing to undecidable with just a single construct like this, which is very useful and quite important in a practical context. Another thing that we introduced, and this is effectively a map-reduce construct in a very declarative context within an imperative language. And this is, again, riding on the idea that a finish is an enormously powerful construct. So what do you want to do? You want to be able to write code that runs in parallel over whatever kind of data structure you have, generating values. And you want the reduction of all of these values. What is your basic problem? You need to be able to specify this reduction operation, and you need to know when that generation has completed. But that's what finish does. So it's very simple then to design a variant of finish, which is an expression that takes a reduction operator of the appropriate type. And then inside it, you use all the constructs I have talked about to spawn your computation one place, many places, as much asynchrony as you want, or you don't, and then use an offer construct. So unlike sequential stuff where you're going to use the stack to return values up, here you use an offer construct to return a value up to your waiting finish. Remember what I talked about exceptions. This is just the same idea, except that it's user-defined code returning real values rather than exceptions. What happens is that the finish will return the set of these results reduced by this reducer, And we give you no guarantee about where and when this reduction happens, because obviously we wish to implement it enormously efficiently in terms of combining results even at the level of activities, the level of threads, and then the level of a place, and so on, hierarchically composing these in the implementation. All right, so the key semantic properties that we have for the language are, this first one was established right early on, are that multiple places, finish, async, atomic, at, clocks, all of these, deadlock free. You can write any code you wish, you will not get a deadlock. The only thing that introduces a deadlock is
the conditional atomic block. So when I say atomic, I mean a conditional atomic block when CS where C is true. Yes?
So I have a question about this. I mean, that sync finish introduces this structure. I mean, it's more restricted than the for join, so you get some good properties.
It's not more restricted than fortune. What do you mean? How is it more restricted?
It happens before graphs, like you get series parallel graphs. In that sense. And so the analysis, some analysis gets more, you can do it better complexity. But the question is whether these clocks, you can actually restrict them a little bit.
Yes.
The structures that they allow so that you actually get still decided for.
Yeah, that would be interesting to figure out how you could further restrict clock. I mean, this has got to be a huge space of interesting programming constructs between this big gap that I talked about. So yeah, I have not seen work. I mean, Sarkar's group has gone off and done other really complicated extensions to clocks. I'm not interested in those. But in this problem of from here to infinity, is there stuff in the middle? I'm very much interested in. Okay, that's that.
There is a concept of clocked final variables that we introduce. You can obviously start with final Java or final X10. All your variables are immutable, and you will not have race conditions. But what you can do with clocks is you can introduce a somewhat weaker regime that says variables get assigned once in each clock phase. That's clock final. And that lets you express a lot more programs, in fact, streaming programs can express quite nicely within an imperative syntax in X10. C10 is a new project we have started, going back to the roots of doing concurrent constraint programming as an implicitly parallel language, compiling out to X10. C10 has no explicit concurrency, no explicit distribution, and it's intended really for AI problem solving, writing constraint solvers, and lots of stuff like this. There's a formal operational semantics that came out in eCoop just now, and the equational theory that we developed, and also for the resilient aspect, and I'll talk a little bit about that. This was a very important thing that we did. We bit the bullet and attacked the hard problem of designing a form of constructors which do not allow this to escape, but which are still usable in practice. And that's all described in the eCoop paper. Yoav Zibin led that work. And I mentioned this thing. And of course, it's the fact that we have async, at, orthogonal, the fact that we don't, unlike UPC, which is a competing language for us, we do not allow a user code to just arbitrarily go and read the memory of another place. You have to use an at to go to some other place. That introduces a rigor which let us just add in resilience without doing very much at the language level. Applications, what exists? A lot of stuff exists. We have a global matrix library that's used by large chemistry codes that has a distributed implementation of sparse and dense matrices, vectors, operations on them. We've got a global load balancing library where we showed numbers much better than anyone else has shown for doing very unbalanced computations like the unbalanced tree search problem, which is an analog of the n-queen search. You're searching for the total number of solutions for a particular n. You get an extremely unbalanced tree, and you've got to load balance it across 50,000 cores efficiently. So we've got efficiency over 90–95% for different kinds of trees compared with a single core going up to around 50,000 cores. Graph library. More importantly, we've actually also, and this is I'm very proud of, we've actually made it happen that a research language like X10 having an impact in IBM in the context of products that IBM is shipping. And in fact, this actually just got announced. So if you don't believe me, you can go to a done website, and you can actually, not that website, okay, and you can actually download a product from IBM. Now you'll have to pay through your nose. That's a whole different problem. And it's a very different thing. It's a piece of middleware that handles a large number of incoming events, keeps state in memory, and runs analytics across that state in memory in a scalable way so you can simply add more capacity and grow things out. Imagine in a cloud context, you've got millions, hundreds of millions of messages coming in simultaneously that you need to process. That's the sort of thing that that is designed for. Main memory MapReduce, another thing that is having commercial, that is going to be shipped with products from IBM. It's an implementation of Hadoop, but in a context where data is kept in memory. So you do MapReduce, we actually run Hadoop code. This was the hardest part of the project, was getting Hadoop to run on our engine. Writing a main memory MapReduce engine, just that, in X10, is about a few hundred lines of code. But getting Hadoop to work on it was a few more thousand lines of code. So there's a lot of real stuff. I will give you a very quick example of the power of in-memory computation. You have GPUs now. People need to use GPUs to accelerate Java workloads. How do you do that? Particularly if you've got a MapReduce computation, how do you do that? You try and you run Hadoop on CPU, that's this level. We're taking as benchmark, this stuff was shown at NVIDIA by IBM, by non-research team at IBM that used M3R to get these numbers. Run it with Hadoop on CPUs, that's the level of performance. You just throw in mappers that are going to go talk to GPUs. You don't get much of an improvement. You run the code on M3R, you get a 3x improvement. You run it on GPUs, you get substantial improvement. And the problem is that there's all kinds of sequential overhead in MapReduce jobs running on Hadoop that go away when you're running it on top of main memory MapReduce with caching turned on. Okay, all right, now let's get to resilience. So as was brought up earlier, the world has realized that particularly the value of Hadoop is not the programming model. It's not MapReduce. That's very, very simple. The value of Hadoop is that the execution engine knows how to recover from failure of a node running a mapper, reducers, and so on. So that the user programming model is utterly simple. Provide sequential pieces of code. They will live within this parallel application framework. They will scale out. Your data has to scale out, of course, for this to work. But the system will take care of everything. You don't have to worry about this. That's the value of the Hadoop programming model. At some level, fundamentally, the value that we are striving towards with Resilient X10 is Hadoop is a particular implementation. And now in Hadoop 2, they're refactoring everything, but it's still dozens of thousands of lines of code written on top of, roughly speaking, from terms of levels of abstraction, it's written on top of very, very primitive things. X10 has already introduced significant layer of abstraction while preserving efficiency. So is it possible that what we could do is move to the context where a variety of these application programming models, parallel programming frameworks like Pregel, like Hadoop, bulk synchronous parallel, like various kinds of graph libraries could be written in X10 and in Resilient X10, so that the Resilient X10 implementation carries most of the workload for ensuring that computation can restart in case of node failure. That's the promise that we're working towards, unlike most of our colleagues who are working on specific separate, like the Spark guys. They have a particular abstraction. Our goal is to do a Spark-like abstraction in X10, Resilient X10, hopefully in very small amount of code, so that you get the performance and you also get the programmability that you get when you have a full programming language available to you. So what is the current view of the world? Non-resilient stuff, MPI, normal X10, any place that if you're running a program and even a single place crashes, the whole program comes down. There's nothing, you cannot recover, it's catastrophic. The other side is you've got Hadoop, you've got various other techniques. In MPI, what you end up doing is you periodically checkpoint your application state so that in case there is failure, you have a state that you can roll back to all manually. There's no support in any language. MPI is an application library. And so that's the transparent fault tolerance view. Where we want to be is this, that Resilient X10 provides those abstractions with which you can program whichever kind of strategy for recovering from failure that you may wish to have. And of course, you cannot really ignore failure. This is a very simple calculation that will show if you wish to run analytic jobs. And now let me point out, the reason we kept Java as a backend is we're not interested in just running on supercomputers. The product impact I talked about is all through the Java backend, running in JVMs in the context of middleware. So there the issue is analytic infrastructure. You're writing, so now the classic example of analytic infrastructure is stuff from is deep learning in the context of billions of variables that you've got to learn probabilities, you've got to learn weights for. You have to go up to hundreds, thousands of cores. You have to go to GPUs to get real performance. So our goal is to be able to write that kind of code in a context that's industrial strength and you can ship. So for that, you need to have some abstraction for resilience. So here is the overview. What we do is simply this. We let places die. We do not change anything at the language level. And that turns out to be possible because of what I told you earlier. There's an arm's length relationship between computations activities running at different places. An activity may have a global reference that points to data there, but it cannot do anything with that data other than use at to go over and do something. But that at provides us with that choke point where if that place is gone, what should happen? Obviously, that at should throw an exception, a dead place exception. So any attempt to start a new activity at dead place will immediately meet with a dead place exception, which the programmer can deal with, can capture and deal with. Okay? So that's the basic idea on how to actually surface a failure of a node in the system. The other problem is, so of course, what was at a place? Remember what I said earlier. At a place, you had activities and you had state. You had heap state, you had the state in the activation frames of these activities. All of that just vanishes, so to speak, instantly vanishes. So, and none of that is going to come back unless you had taken some steps to preserve some state. The problem is that it's not just good enough to say that that place has died. Because we have this very expressive programming model, and I mentioned to you that you can have a finish that has an at inside, you go to another place, and that can recursively have the same structure. So this place dies, but before it died, it spawned a whole bunch of activities at other places. So these guys have died, but those orphans remain. And you've got to figure out how to deal with those orphans. That is the hardest conceptual problem in defining resilience for a programming model which is as unstructured at some level as X10 is. So I'll tell you how we do that. And this is where the HBI principle that happens before invariance principle comes into play. So the other places will keep continuing to run. There may be more failures, more places may go away. It's a very natural extension that we are working on. We don't have papers on this yet to say, just as you may fail and places go away, you may also wish to be elastic and new places can arise and join your computation, and existing computation can now spread over these new places. So the goal of this project that the Air Force is funding for us is to do both a resilient and elastic implementation of things like MapReduce in the context of a language designed to deal with it. And again, application level failure recovery has got all kinds of interesting properties. You wish to have this because you can now make trade-offs like this man said a long time ago. You need to be able to deal with some computations which are such that it's absolutely okay for a portion of the computation to just vanish. I'm doing a Monte Carlo simulation. I need to do lots and lots of probes. I need to do an average over those probes. If some portion of those probes just vanish, that's okay. I'll get a worse approximation, but maybe good enough for what I need to do. So the programmer is the one who knows this stuff. He's got to be able to write code that does that. In some cases, the computation is repeatable. We can just replay. In some cases, there's lost data that you need to access. Well, okay, you can just reload it in a new place that has started up to do this computation. If data is mutated, you may use a checkpoint scheme. And again, because X10 is built with object-oriented principles and therefore has building libraries is a really big deal, it becomes possible for us to write code in libraries that hides some of these decisions. So the users, once again, may have something as simple as a MapReduce implementation, which transparently does resilience handling. But that's not a property, that should follow from the properties of a small piece of code written in resilient X10 to implement that programming abstraction. All right. And I've covered the rest of the points. Now let's get to see how it actually works. Ignore the rest of it. This is a program. This is a program that shows you something fairly simple. It's like a collect and finish. You start with main. You create a new cell at place 0. Computation starts with a single activity running at place 0 that's running the body of a main. You create a global ref to a cell, store it in C, start up a finish, inside it loop over all places, asynchronously go to them, and do some non-trivial amount of work here. When you have your result, you go back to the first place, which is place 0. You dereference this cell using the reference that you got when you went over to that other place, and you atomically update that cell, summing this value V in. Let's say this is a schematic computation that you wish to perform. And then, of course, once you are done with it, this finish will tell you you're done with it. Now you want to print out the cumulative value, okay? This is a very simple thing that you wish to do. It's a common pattern, as I said, for the Monte Carlo example that I mentioned. And what can happen, and these graphics are all due to David Cunningham, what can happen is, poof, a place just dies. So you lose the heap, you lose the activities. And any at that is running at that place is now going to throw an exception. It's a synchronous context, it's going to throw an exception. The place is never going to come back alive. You can no longer do an at to this place. If you do, you get a dead place exception immediately. And you still have global refs that are pointing to this. But those global refs are essentially dangling, and it's okay for them to be dangling, because any attempt to use them has to use an at, and then you're going to throw a dead place exception. Okay, and we provide new APIs that let you figure out whether a place is dead and get the list of alive places and so on. So the program that I showed you, this is an X10 program. In case there is a failure, this thing will just crash. What if we wanted to write the version of this where if a place crashes, you simply lose the computation that was running at that place, but you keep going with the rest of it? So that's what it looks like. The only thing I've done is I've added a try-catch block. So now you're running at place P. If that place dies, there will be an exception thrown, which will be a dead place exception. This try-catch will catch that, drop it on the floor, do nothing. Rest of the stuff keeps running. The results from the rest of the stuff will keep coming back to first place, and they will get summed up, and you will print your answer out here, even if a place crashes. So now let's take a look at what happens before invariance, why is it important, and how does it help us. So this is the key insight, and I have to say it took us actually many weeks before we figured out that this is the basic idea. The problem is the following. I told you that a place can die, but if a place can die, you get these orphans. So a finish starts off stuff here. This is going to start off activities at some other places. This stuff goes away. These orphans still exist. And these orphans are important because, again, unfortunately, everything is based on mutating shared variables and partition global address space. So these are running around, and they are happily executing their code that is mutating stuff. And we already saw that there's a finish sitting up front, which has code running after it, which is assuming it is going to run only when everything inside has finished. So then it's pretty obvious what you need to do. Even if a place dies, you've got to preserve the happens before edges for the activities that remain. So you're not introducing new races just because a place died. Very simple idea. So that's HBI. And so here, what in the implementation, so it turns out very simple to state, and from the usage point of view, this is sort of what you expect. So there's nothing really to explain to users about how your model has changed. But the implementation is, again, a bear. Because what you've got to do now is you have to figure out that when, and there may have been a finish here, by the way. I'll show you examples where this becomes really complicated to figure out. That's why we actually needed an operational semantics, a formal semantics, to make sure we covered all the cases. You can have a finish here. So this activity is actually controlled by the finish here. So what it's supposed to be doing is if, when this is returning a result, that result, for example, it throws an exception, that should come here. The finish is supposed to collect it and then throw that up here. But now all of this is gone. And we still need to ensure that this must terminate before this finish continues. So on an operational point of view, we are faced with formalizing and implementing the notion that some control information has to be preserved, that which deals with the global distributed control constructs, namely finish in this case. There has to be preserved in stable storage, in storage that outlasts this place completing, and that may be either a specific place like a single place, place 0. We've done that implementation where place 0 is our designated place, you send data back there, or in the distributed implementation where you're copying the state out into multiple VMs. And so one place dies, but before you commit to doing, to executing this activity, you have recorded the fact that you've got a new activity in your stable storage in another place, and you can reconstruct and patch the finish call graph, finish async graph, after that place fails. Okay, so there's lots of work to do in the implementation. Here are subtleties. If I have an at, go to place 1, do a finish, inside is an async s, then clearly given the semantics that I've discussed with you so far, s will happen before q because async s must finish before this guy will finish, that must finish before at must finish, that must finish before q will start. So that's what happens before. But you can have a finish outside. Within the scope of the finish, you have a queue. That finish is not important. You go to place 1, you do a finish async like you did before, but you put an async in front of it. Now, this thing is running. In place 1, this thing is running, and as soon as you've spawned this thing off, the at returns. The at returns, you're going to execute the queue. So Q and S are running in parallel with each other. Okay? And in both of these cases, if place 1 dies, you've got to do the right thing. The right thing here is not waiting for, is not saying, hey, Q, you've got to stop until S completes, because that's not what the programmer wrote. You've got to let S and Q work in parallel. There is more subtlety around exceptions. We ensure that actual exceptions that get thrown by code that are going through failed places, you've got to mask them. And we mask them by replacing them with dead place exceptions. And the reason you've got to mask them is because the user may have written handler code for that exception. And that handler code was supposed to be running at the dead place, but the dead place is gone. All the state associated with that handler is gone. You can't run that handler. So instead, we mask it, we promote, so to speak, everything to a dead place exception. There's no additional context you get to the dead place exception. And so that's a subtlety that you need to be aware of. How are we doing on time? I have, okay, we're going to the top of the hour, right? We're going to 10? Okay, so I have about 5 minutes. Yeah. Okay, so let me quickly tell you the issues around formalization. So again, I started my life, so to speak, as a computer scientist working with concurrent programming frameworks and the semantics thereof. That's how I got to meet this guy in '89. Yes, he did his first Popple paper with me. Yes, first two. Sorry, '88, '89. Yeah. Whatever. Yeah. Okay. Done. Okay. So what's the point? The point is, I would love to do an appropriate denotational semantics for this, and we may still at some point do that. But our goal here was very straightforward. We were running into all of these complications about what the heck does it mean when you got finish async at and you're spawning things everywhere, and you want to preserve a happens before relationship. Let's just try and formalize this. So we went back to very simple things. I've also done a fair bit of work on weak memory models. Forget that. We're going to work here with sequential consistency, and what we're going to try and do is simply model what happens when a place fails. So to do that, what do you need to do? You need to abstract away, get a theoretical X10 that has the usual things, but we have to do enough to make sure you preserve all the constructs you care about. There's a skip, there's a throw, there's some evaluation of expressions and bindings of variables introduced in a statement as assignment. You've got to have. You can't do the thing that featherweight people do when they do type systems. You've got to have assignment, because this whole thing is about assignments and how you got to preserve the right properties that happens before relation. You got sequencing, you got an at-p, async, finish, try-catch, you got exceptions. Everything works based on try-catch. You got to get try-catch in. And then you need and this is a little bit of inelegance, you need the kind of dynamic version. It turned out it's crucial to make the distinction between an at statement that is available for execution and an at statement that has actually started executing. Particularly because of failures, you have to make this distinction, and similarly with an async. Here was the key that makes things work out very simply. I had earlier done an operational semantics for X10, where we had worked out that what we really want to do is keep our configurations as simple as possible. Let me emphasize. The problem here, even the conceptual problem, problem from the viewpoint of modeling for semantics, is that you get these arbitrarily complicated trees of activities that are partitioned into different places. And you've got to preserve that notion. And you've got to have these finishes which keep track of just the tree underlying it. So you've got to do that. So how do you do that? My friend Jens Balsberg did a pretty complicated semantics where you end up in essentially introducing these complications I talked about in the structure of your configurations. That's a nightmare to work with. What we've done instead is to say simply, hey, our configurations are what you would find in Plotkin's notes from '82. It's a statement and a heap. That's it. And of course, when the thing terminates, you get a heap. The heap is a global heap because the heap is going to contain state at each of these places. So it's a sort of a tagged place and local heap. And so the entire trick, if you will, is to write these rules in the structural operational semantic style that go up and down the syntax of S and tell you precisely what should happen when these weird things take place. So what do you get? Oh, and Avi Shinar in my group actually went off and did a bunch of formalization in Coq to get several of these proofs to work. So here is what happens. Our transitions look like this. You go from SG to S prime G prime. Label it with the place at which that activity that took the step that caused this to happen. Label it to that place. Or you terminate, and then you've got to deal with exceptions. And so what you deal with is, oh, an exception got thrown here with some value, E. And now you've got to deal with this notion that this exception is one of two kinds of exceptions, either a synchronous exception or an asynchronous. What's an asynchronous exception? Remember I said, so an async throw V. Throw V will throw an exception, but it's going through an async. So when it goes through an async, it's headed for the finish that controls that async. It's not headed up the sequential control stack. Whereas when you throw an exception in Java or you throw a synchronous exception here, you got a throw V, no async. That throw V is going to unwind the call stack. So that's a synchronous exception. So you've got to distinguish these two kinds. And here is an example of what these two kinds of things. And synchronous failure, when you propagate that, obviously, if there's any synchronous continuation, that's waiting for the previous thing to finish, the previous thing through an exception, that continuation has to be wiped out, but not with the async guy. Okay. And what we established was the usual things that the semantics make sense. It's all no stuck states. And in fact, we get an interpreter for TX10 because Avi formalized this in Coq, and that gives us an actual operational semantics implementation. So what do we do with failure? That's all. Here's what we do with failure. At some level, that's all. Place dies. What it place dies, what is the change? Nothing changes in our statement structure. The only thing that changes is the domain of this global heap changes. You remove this place, it's no longer there. Single step, you say place is gone. Okay. Now you've got to figure out how each of your statements are going to operate if they are running at a dead place. So B is not in my domain, it's a dead place. If it's a skip, throw a dead place exception. You cannot execute code at a place that is die. Similarly, if you're trying to, again, remember, this is the async that is waiting to be scheduled. It hasn't been scheduled yet. You cannot take the step to schedule it. So you're going to throw an exception. Similarly with the at. What did I do? I went back. Okay. All right. And this is effectively all. There are a few more rules that you need to know about to actually get everything formalized. But I've captured the basic ideas for you. And then our main theorem is that in fact happens before invariance is preserved by the formal language that we have. And there is a simple example you can work through with the semantics to see how this whole thing works. Let me stop. So resilient X10, we are very excited about this work. So Martin has done work in Jade a long time ago. And with Jade, you had the ability to recover from failures in the implementation. And Jade programmer was unaware of the fact that recovery happened, right? So here we're trying to not do that. We're trying to let the programmer be aware so that the programmer can write application frameworks on top of it so that his programmers are unaware that stuff happened, okay? And so, it's a complicated point. Getting everything to work. Semantics is easy, a few months, paper, done. But now you need an implementation that works. Particularly, you need a really efficient distributed finish implementation. So we have efforts going on. We have preliminary numbers. We reported some at PPOP. Now we're doing it for real so that actual X10 users can start using that. And we're not done there. There's still work to do all that. We have many examples in our PPOP paper in this year which introduced Resilient X10 that show that you get good numbers, certainly compared to Hadoop and stuff like that. And what is a talk that does not end with the same two cats? Questions?
Questions? Yeah.
I have a question. So, in actors models, they usually deal with resilience by having a supervisor for a place. So they don't throw exceptions because they claim that they don't want to try and catch all over the place.
Sure.
So how do you compare these two?
I mean, we could implement that in this scheme fairly straightforward. Once again, what I said is Resilient X10 gives you this procedural framework where you can precisely deal with failed places. Now, how you surface it to real, actual programs, the kind that like JavaScript, that always works, is the second layer of abstraction. One of those could well be the Scala style, Akka style, you delegate to somebody and let them figure out what you do. That's fine. They're playing a different game, you're playing a different game. We want to deal with language at the base level with efficient implementation that can deal with these things.
Yeah.
So the throwing of the exception when a place is already executing something and it dies. So does that happen? So does that mean that the caller has to continually monitor?
So that's absolutely right. Any act that you write in code in Resilient X10 could fail. So you've got to figure out how if you're writing at the Resilient X10 level and not at a framework level, right? Then you've got to figure out how to deal with it. And and doesn't mean that you've got to necessarily deal with it with the try-catch around that act. You could deal with it at a surrounding context, but you've got to reason about it. So that was the decision that we made in X10 was we're going to force the programmer to reason about distribution, about concurrency, and now we're saying about exception. But we do some work for you, not all.
This reminds me of Peter's talk yesterday where, you're on the phone and you're doing all these checks, but then various weird things can happen and, the checks are no longer valid, right? The connection here is that you fork out a piece of work that's supposed to happen at some place. Half the work gets done and sort of mucks around with the global state in some way.
Yeah.
And then the exception happens. Have you thought about what are reasonable design principles?
Absolutely. That's the sort of next steps that we're going to do. So obviously, the first thing to do is to note that the stuff that you forked out, the simple case is it's mutating only stuff at that place. And there's no problem, that stuff is gone. But the complicated situation is that itself needed work done elsewhere, and that work stays. So we've captured, all I've told you so far is that we captured the HB relations and preserved them. So at some level, what you've said is the state changes that you wish to happen, some subset of them have happened. And you can precisely, once you understand when the exception was thrown in the place, right, you can figure out which things happened and which things didn't. We leave it up to you to recover from that. That's maybe good enough at the Resilient X10 level, it's not good enough at the next level. So now we're working at the next level, which is, I mentioned global matrix library, GML. Abstraction to a programmer is like an R programming. You've got these distributed matrices, do, multiply, divide, add, whatever. But then we don't want to expose any of this. So then we've got to have a way where we either transparently checkpoint and say, and we have stuff working in our trunk right now which does that, or the user gives you some hint about what is important, what can be recovered. So the RDD stuff from Spark, for example, we expect to be able to redo that on top of Resilient X10. So there's a second layer of design that has to happen for getting many of these idioms working, so that they're much easier to use than doing everything from scratch.
Any more questions? Armando again.
So if you spawn something at place 1, and that spawns something at place 2, and then, so if place 2 dies, the exception goes to place 1, gets caught. But if place 2 and place 1 die at the same time,
Right.
then you're going to get an exception at place 0, that originally launched place 1, but it's only going to know about the failure of place one, if that works?
It is going to get a dead place exception, which now I wish I knew the answer, but I can't, I don't. The dead place exception, of course, carries an argument. And I don't know what information that argument carries. So whether there's a nested dead place or not, I can't answer that right now.
Presumably it doesn't matter, because if you died at dead place one, means stuff you wanted to do.
But the issue is there's stuff elsewhere.
Yeah, I guess the question is, so if you know that you died at place one, you know, okay, I have to recover the data that I have at place one.
Right.
But if you died at place two as well, and you
Yeah.
didn't know it,
So
and
let
you
me-
didn't find out.
Again, let me just re-emphasize the answer that I gave. I think our work at the foundation level is a little bit incomplete. We've got HBI, I think that's important, but now we've actually got to also deal simultaneously with memory disciplines and how those get preserved across this time. So HBI helps us there, but doesn't take us over. And certainly we're doing MapReduce style stuff where there are no side effects. It's far easier, and I expect we will be able to establish theorems that say that for classes of computations with these structural properties, this memory recovery regime is adequate to, transparently deal with things.
I think one benefit you have in the distributed systems is generally all your
Why don't you
states
come in?
kept in the database, you have transactions, and.
Yes,
and then-
so that is actually correct. So there's a variant of what I've talked about that I call grid X10 that we're working on, where your states updates, we use the atomic construct of X10 to actually do state updates atomically. And in a way where when you commit, you're committing to multiple places because you're replicating the state in multiple places, so you get resilience out of that. So grid X10 I expect is going to be one of these abstractions on top of resilient X10, which gives you a view of computation similar to what people do today in grid computing, where, again, their key value stores are distributed all over the place and they're resilient to failure, so the transaction will just get retried at some other place and just work.
One question here, Vijay.
Yeah.
So I think you mentioned Yanko. This is the
Yes, yeah.
people vector, right? So there the state gets complicated, right?
Yes.
And this model is three-sided, if I remember, right?
Yeah.
And here you don't model them?
I said this, we have precisely the same language that you have.
Oh, the same thing,
It's the same stuff. The difference is the way that we deal with our configurations. So that just dramatically simplifies the formal complexity of doing your operations system. So if you are going to do anything formal in this case, I suggest you start with ours. You'll find out pretty quickly that that's much better.
Okay, so let's thank Vijay.